Chapter 15, Interfacing to the Analog World. We'll discuss digital and analog representations that will solidify your understanding of changing into the analog world to the digital world. There are 4 binary positions of 4-bit resolution, which means there's 16 different representations of the same 4-bit value. In an 8-bit value, you would have 256 different representations. This diagram here shows you an analog voltage over time, and corresponding you have your analog voltage levels and your digital readouts that correspond to your voltage levels. So you have 3 volts for analog, you have a 0011 for digital, which is a digital output level 3. Operational amplifier basics. An op-amp is a very high input impedance device. It has very high voltage gain and very low output impedance. This is a simple op-amp circuit. You have your 5-volt source going through a 10K resistor into the negative side of the op-amp with a feedback resistor of 1 kilo ohm. And through the formula we can see that we have an output of negative 0.5 volts with our amperage at 0.5 milliamps. The Vout equals the voltage across RF, or feedback resistor. Binary weighted to digital to analog converters. These are the sum of the currents from the input resistors. It's a binary weighting factor. And accurate resistance are difficult to obtain. Practical, then the practical for 4-bit conversions at a maximum. This is an example of a switching op-amp with binary weighted resistors. You have your switches turning on and off your resistance. This would create your analog voltages 0 through 15 and your digital voltages also, your digital output levels 0 through 15 as well, through the stepping up of your binary weighted resistors. R over 2R ladder digital to analog converters. There are only 2 resistor values. 8, 10, 12, 14, and 16 bits and higher resolutions are obtained. This is an example of an R over 2R ladder operation. With the step ladder graph going up, you can see you have 2 values per volt. Integrated circuit digital to analog converters. The DAC 0808. This is the block diagram and chip pinout of the same chip, the D0808 digital analog converter. It takes the digital value and converts it to its analog equivalent signal. And this is the same thing, changing it to its analog value. C data converter specifications. It's a differential nonlinearity, has a lot of gain error, missing codes, non-monotonic. There's an offset error associated with this device. Its relative accuracy is a settling time. As you can see here, this is a perfect ADC line. This is a usual high gain and a low gain. But with the dotted lines, you see the ideal, but it's not ideal because it steps up. And the step size error with differential nonlinearity with these nonlinear steps going up, as you can see. And this is another example of the same thing. where you have a missing number here. There should be another step right there. And these are some other examples of the same thing with offset errors and an ideal versus ideal setting through the analog input, because it's very volatile and there's timing issues along with it. Parallel encoded analog to digital converters. Parallel encoding is simultaneous and has a multiple comparator associated with it. Usually a flash device uses this. And this is a 3-bit parallel ADC, taking in the values and outputs your 3-bit digital value, takes in your 0 through 7, your 8 bits, and converts it to a 3-bit number. A counter in conjunction with a D to A converter is the counter ramp analog to digital converter. Some of the disadvantages is slow conversion time, and its speed depends on steps necessary to convert. This is an example where you have your counter, your digital D to A converter, and your 8-bit flip-flop. Successive approximation analog to digital conversion. This is an example of that, with your register, your SAR, taking these values and your 8-bit D to A converter values, combining and putting them through the output register. Integrated circuit analog to digital converters. Another example of these is the NE5034, as shown here in our block diagram, and the ADC0801. It's another integrated converter. A data acquisition system application. This is a system that takes in values and outputs in data from various systems, such as various sensors like temperature, pressure, displacement, velocity, and many more. And it takes those values and outputs those through the microcontroller, and you can record those values through interfacing to a computer. Transducers and signal conditioning. Physical quantities to electrical quantities. It must be conditioned. Thermistors. The resistance dependent on temperature. Response is nonlinear. This is why you need your signal conditioning to make it a linear and more constant curve with your op-amp signal conditioning circuitry. Linear IC temperature sensors and the strain gauge are also the same thing. With varying resistance, they must be signal conditioned to get the right gain and to convert to a D to A converter. So in summary of chapter 15, we have any analog quantity can be represented by a binary number. Binary weighted D to A converter is the simplest to construct, but it has practical limitations in resolution. Op-amps are important building blocks in analog to digital and digital to analog converters. They provide means of summing currents at the input and converting a current to voltage at the output of converter circuits. And your most common is the D to AC 0808 IC, which is an 8-bit A to D converter. Uses the R divided by 2R ladder method of conversion, the step size. This will allow you to have your 256 unique binary values and equivalent analog voltages. And applying an 8-bit counter to the input of an 8-bit D to A converter will produce this 256 step sawtooth waveform at its output. And the method of A to D conversion used most often is called successive approximation. In this method, successive bits are tested to see if they contribute an equivalent analog value that is greater than an analog input to be converted. If they do, they are returned to 0, After all bits are tested, the ones that are left on are used as the final digital equivalent to the analog input. And lastly, the data acquisition systems are used to read several different analog inputs, respond to the values read, store the results, and generate reports on the information gathered.